Let's continue discussing surface integrals. Okay, let's review what we have so far. So we're trying to look at the double integral over a surface S of f of x comma y comma z ds. It is important to note that the s here should be a scalar s. I know this sounds a little funny, but there's no arrow on this like in the lowercase r. Okay, so scalar s here, not a vector. And when setting this up, there's two pieces. So there's the S part. So there's the surface S. Okay, and let's leave a couple lines to talk about that. And then there's also the function that we're integrating, f of x comma y comma z. So there's these two separate things that need to be provided. Okay, there's the surface S, and then there's the function f of x comma y comma z. So let's go back to the surface S. There's fundamentally two ways that S could be described. So if S, so as one way to do this, if S is parametrized by vector function r of u comma v, then the ds eventually later gets replaced with the magnitude of the cross product of the partial derivatives r sub u times r sub v du dv or dv du. We'll just, for simplicity right now, not write both of these. So du dv, let's just say. The other way that s could be described, though, is if s is the graph of z is equal to g of x comma y. So by the way, we use a g here. We use g of x comma y to not confuse this with lowercase f of x comma y comma z, which we still need to talk about here next. All right, so if we're talking about the graph of a function of two input variables, then eventually later ds gets replaced with root 1 plus the partial derivative of g with respect to x squared plus the partial derivative of g with respect to y squared. And then, again, a dA, but just for now, we're going to write dx dy. This could also be a dy dx, or you could have polar coordinates or whatnot. Okay, so one thing you need is a surface. The other thing you need is a function f of x comma y comma z. So far, we've already seen three possibilities. So what is f of x comma y comma z? Well, it depends. Maybe f is just given in the problem, right? So maybe the problem, for example, starts with the language like this: integrate f of x comma y comma z equals x plus y over z over some surface, blah, blah, blah. Language like that. Or second, maybe you're asked to compute surface area. So for the surface area of S, a question might just say that. Then you just need to use f of x comma y comma z is the constant function 1. If you were asked instead for the mass of S, then use for lowercase f the density function, which is often just called like a lowercase rho. Now, if we're going to actually now, what we're going to do is we're going to add to this story right here and have two new options. That's just a preview of what's going on. So what are we about to do now is we're going to throw into this mix something in addition. So if you have capital F arrow, so this is a vector field now. Okay, so if we haven't mentioned that yet so far today. So if F arrow is a three-dimensional vector field, we will build, just to preview where we're going here, we will build two additional integrals of the form double integral over s of f of x comma y comma z d capital S. However, with these two additional integrals that we're about to discuss, but these integrals, okay, these two additional integrals will only make sense if S is oriented. So S needs to be oriented or orientable. So surface S needs to be oriented. Okay, what does this mean? So the official definition looks like this. The surface S is orientable if there is a continuous function. It is important that this is a continuous function, not just any function. Okay, a continuous function, we'll name this n arrow. Okay, so this is a vector function. The domain is the surface S. The codomain is v sub 3, or roughly speaking, if codomain is a strange word to you, just call that range. We'll talk about what this, well, let's just do this right now. This v sub 3 is just meant to be the set of three-dimensional vectors. Okay, so you need a function where each input, an input is an element from, is a point on the surface, and each time you have a point on the surface, the output is a three-dimensional vector. Okay, such that the vector n of x comma y comma z is a unit vector perpendicular to the surface at the point x comma y comma z. In addition, we call the function n arrow, we call this an orientation on S or of S. Roughly speaking, I know this is a little much to take in right now. Roughly speaking, S is orientable if S has two sides. This two sides business is more like an everyday language. So let's take a look at some examples. All right, so I've got two just little strips of paper like this. I'm going to take one of them and I'm going to just take this and then tape it like that. And then the other one, I'm going to just insert a tiny little twist in there and tape it like that. Okay, BRB. Okay, so here we go. Here's the first of these. Just a nice kind of band, kind of wrist bracelet type thing like this. And then the other one here has a little bit of a twist. This is called a Mobius strip or a Mobius band. So for the first of these, this is an example of orientable. So what we can do is at each point on here, so every single point, maybe I'll just use this marker for a second. At every single point, I'm just drawing a couple quick points there on with this orange Sharpie that I have. At each point, there needs to be a vector as output for this function. And the thing is, this function needs to be continuous, this vector function called lowercase n. And so to represent that, I've got this right here. So this is just, it's just a barbecue skewer super glued to a suction cup down here. And then I just put some Play-Doh at the top right here. That Play-Doh eventually keeps falling off. So I gotta, so the point is at each point down here on the, on this sheet of paper, on this what I claim to be orientable, is we need to make as an output for the n vector, and then you'll see that as you do this and go around like that, there is you come back right to where you came with no abrupt change in the output of this function. Now, to really demonstrate that this is orientable, I can take a marker, and if I start drawing on some point here, and let's say I'm going to paint the entire thing like this. Let's hope I don't get a paper cut doing this. Yeah, then, oh, we end right back where we started. And you'll see that this thing has, well, two sides, because there's the side that I marked. And then on the inside, yeah, you see some marking, but it's just because it's kind of faint and because the um, the Sharpie has bled through. Now, if I take the Mobius band, the twist that this thing has is going to change things up. So if I start drawing somewhere, so maybe I should try to show where I'm doing this drawing. As I keep drawing, and this is just a little awkward because of eventually, as I keep drawing around, I'm actually drawing on the side that has bled through with the marker before. And as I keep going and I keep going and I keep going and I keep going like this, I actually end up right back where I started. So this is an example, this Mobius band or this Mobius strip is an example of a non-orientable surface. So far we had the example of the strip of paper that, looked something like this. And we'll just sort of draw the back edge of it like that. So this was an example of orientable. We had a non-example of orientability, and this was a Mobius strip. So this was essentially the same kind of shape, except maybe in the front I'll attempt to draw in the twist that occurred here. So something that looks like that. And then here's the back edge of this. So this is the Mobius strip. There's actually umlauts on the O, so this should be actually pronounced Mobius strip, or Mobius band. And a note just to make right now is that if n, so that's this function up there, if you have an n function, okay, if this is an orientation on a surface S, then in fact negative n is also an orientation. So think of it sort of like if n is marking one side of the surface, then negative n is like the Sharpie on the other side of the surface. Let's also take a look at another example. This one we're just going to draw. So what if S is the set of points x squared plus y squared plus z squared is equal to 1? You know that surface, right? That is the sphere of radius 1 in three-dimensional space. So let's see, x-axis, y-axis, z-axis. So we have this sphere here, and there's at each point, to draw n, there's at each point on the sphere, let's say you have an arrow pointing outward. So this would be the outward orientation. And so each vector that you draw is perpendicular to the surface, at least in an instantaneous sense. So imagine like the Earth, or the crust of the Earth, and then these arrows that you have pointing upwards or outwards are, let's say, buildings of all the same height, and all of the buildings should be built perfectly perpendicular. None of that Tower of Pisa business. And then if negative n is also an orientation, then so if this one's let's say n in this case, then n arrow negative, this would be the inward orientation. So you could, I know this sounds silly, but imagine all the arrows now pointing inward, or you have buildings of all the same height that have been built into the ground, let's say. Let's take a look at a couple more examples. Okay, here's another example of a surface that is orientable. So I'm talking about the plastic of a soda bottle. So of course it should be even thinner, right? But there's an inside and an outside, and I don't even mean the part where the soda normally lives inside the bottle as being the inside. What I mean is on this surface, this plastic, there's a side that I'm touching, and then there's the other side of that plastic, which is inside, right? So here, in outward orientation, you could have your end vector doing this. At each point, you need perpendicular to the surface, so something like that, right? And so this is orientable. As another example of an orientable surface, how about a cheesecloth? I couldn't find my cheesecloth, so I just, it's a cloth with a bunch of like very, very fine-grained holes in it, but I just have this, tea towel or kitchen towel here. And this is orientable because there's, however you freeze this in place, there's a this side, top side and a bottom side, for instance, right? So we'll actually come back to this example in a moment. And then as a final example, I have for you here a T-shirt. Now this shirt, I actually have, you see the tag sticking out here. This shirt is inside out. Um, when teaching on this day, I actually do intentionally normally wear a shirt inside out. And somebody will usually eventually point this out. And this is where I say, hey, thanks for noticing that a t-shirt is an orientable surface. So this is one orientation. In fact, I could take the arrow thingy here and just attach at each point here that the arrow should be perpendicular in an instantaneous sense to that point on the surface. Okay. And this is, I guess, the inward orientation, rather the orientation in towards the body of the person wearing this shirt. And then if I flip this shirt inside out, then is a UWL shirt, of course, right? So then I've got at each point here, you can have that. What the orientation does is it points outward at each spot, okay, even the back of the shirt and so on. And the reason I want to bring up this example is, yeah, this orientable surface happens to have four holes in it, right? The head, the right arm, the left arm, and then at the bottom. And the fact that this surface has holes does not affect orientability. So the existence of holes does not necessarily mean non-orientable or anything like that. So orientability and having holes are two completely separate things.